to welcome you to today's webinar. Our topic, Simulation-Driven Design, Improving Productivity with Fast and Accessible Simulation for the Design Engineer. And I would like to welcome and introduce today's speakers. With us, we have Patrick Farrell and Tim Miller. Patrick brings over 20 years of experience and success in the CAE industry to Siemens. As Senior Marketing Manager in the Simulation and Test Solutions business segment, Mr. Farrell is responsible for worldwide product marketing of SimCenter CAE Simulations Solutions. Prior to joining Siemens, he held product management and application engineering roles. Mr. Farrell has an MBA degree as well as a BS degree in mechanical engineering. We also have with us Tim Miller. Tim specializes in the structural, thermal, and flow analysis products in the CAE Center of Excellence group for Siemens Software. Tim has a mechanical engineering degree and brings over 30 years of experience, with over 15 of those being here at Siemens. We're very excited to have both of you with us here today. Patrick, I'll go ahead and pass you the ball here first.
So again, welcome everybody. Thanks again for taking the time to join our webinar today. As Sarah mentioned, my name is Patrick Farrell, and I'm Senior Marketing Manager for Siemens Simulation and Test Solutions. The age of simulation-driven design is here, and simulation is increasing designers' productivity with fast, accessible simulation. In today's presentation, we'll show how design engineers can take advantage of out-of-the-box CAD-embedded simulation tools that can help you get immediate feedback on your design's performance and rapidly make adjustments for a better design faster. This webinar is also part of a series of webinars that we've been doing on simulation-driven design, and it follows on after two previous webinars that we've done on the subject. So perhaps some of you have already attended one or both of these webinars, and thank you to those that have already done that. But don't worry if you've missed those, because it's also available on demand from the event section of the Siemens PLM website. And just to quickly recap some of the key points of simulation-driven design. Simulation can be used to discover new, unimagined design possibilities at the concept stages of development. Next, simulation can be embedded into your design process to increase design robustness while speeding development processes at the same time to get to product release faster. And you can leverage the scalability of an integrated simulation platform to easily transfer designs and prior simulation data to the CAE team to rapidly validate that products meet complex product performance requirements. And at Siemens, we've removed the wall that has traditionally separated design and simulation teams. And we've integrated our design and simulation technology through the combination of NX and SimCenter simulation technology. Both NX CAD and SimCenter 3D and SimCenter Flow AFD products are based on the NX platform, which means designers and simulation experts can easily share data and technology. This means simulation can be exposed to the design team directly in the NX CAD environment for both conceptual design and detailed design work. And simulation experts can have confidence in the results created by the design team, since they're using the same fundamental technology, and they can even have control over the types of simulations that can be run by the design team. So Siemens can help you implement simulation-driven design in two ways. The first, or one of the ways that was a focus of one of our previous webinars, is the ability to automate advanced yet routine simulation processes so they can be used by designers and design engineers. And it's possible for simulation experts to capture and automate those complex analyses process so that they become repeatable processes using best practices that have already been defined by your CAE team. These routines can be packaged and deployed directly in the CAD environment, so your design team can perform these simulations on their own, which then frees up the CAE team to work on more complex tasks. The other possibility, and the focus of today's webinar, is on out-of-the-box design-embedded simulation packages for basic structural, flow, and motion analyses. These simulation modules can quickly be installed and are accessible right from the NX CAD environment. As a result, these simulation tools are easy for design engineers to learn and use so that they can get immediate feedback on design performance and then quickly revise their designs without ever having to leave the CAD environment. Ultimately, simulation-driven design within the CAD environment gives a designer quick, qualitative feedback about the performance of their designs, so they can make rapid geometry changes and iterations before delivering the part for more detailed analyses by the CAD team. And having a design-centric workflow is one of the key differentiators for ambitious, best-in-class companies today. A unified, consolidated tool such as NX streamlines the product design cycle. So General Motors, for example, is making a push to expose simulation to designers, where they're using NX CAD embedded tools to determine if a particular design is reasonable, if subsequent iterations are improving its performance, or if a change actually degraded performance and should be abandoned. So what do we mean by out-of-the-box CAD integration? We offer a set of simulation tools that are aimed specifically at designs and design engineers, and these cool tools can be added directly into your existing NX installations so that they appear seamlessly within your design environment. No additional configuration is needed. These simulation tools are based on the leading SimCenter solvers that have been used by simulation experts for decades. These help designers in two ways. The first, the simulation technology used within the CAD environment is trusted. And next, the simulation data can seamlessly scale to your simulation experts using SimCenter. This facilitates increased collaboration and communication between designers and simulation analysts to work towards the same goal of creating the best design that meets performance requirements. And our CAD-embedded simulation tools are aimed at helping you achieve the right designs for structural, motion, flow, and thermal analyses. We also have a tool that designers can use that will help you create entirely new shapes that are optimized for structural performance and weight based on simulation results. And this area is called topology optimization, but we're not going to be addressing that topic today. We'll save that for a future webinar, I think, at some point. In terms of the product names for each of these areas are shown here, and each of these can be installed into an existing NX CAD installation and can be launched right within your working environment when you're ready to assess your design's performance. And before we get into a live demonstration, I just want to give you an idea of how a design engineer could use CAD embedded simulation. So let's consider this example where a design engineer is developing a plastic extrusion die. The plastic will be pushed through this die at high force, and the plastic needs to come out the other side at a specified thickness. But because of the large force, there is concern that the plastic could, at the exit, could cause the exit opening of the die to deform, which would mean then that the plastic exiting the die would be thicker than what the requirements call for. So the design engineer can use simulation to verify whether the design will meet the requirements and also assess alternative designs. So in this demonstration, you'll see how a designer can first perform a flow analysis to see velocity results and obtain pressures that can be used on a structural model of the die. We'll also see how a different die design can impact pressure distribution. Next, these pressures will be used to evaluate structural performance of the die and to finally verify if the displacements at the exit will still be in line with performance requirements to produce plastic at the correct thickness. So now at this point, let me hand it over to my colleague Tim. He'll give you a live demonstration so you can see how this process is done directly in NX.
Okay, so as Pat mentioned, my name is Tim Miller. I will be showing you an analysis of this plastic filling extrusion die. This is the model that we'll be looking at, which you see on the screen here. The plastic comes in this square hole in the back, and let me put up a clipping plane here to show you what it looks like inside. So it comes down this angled area, plenum area, and there's actually two different versions of this. The original version that we're going to be working with is basically it flattens out at that point and continues to spread out left and right until it comes out the front. And the design concerns that we have on this, this die are that we want to minimize the amount of deflection that we have up in the front, we want to equalize the pressures and velocities as much as possible of the plastic so that when the plastic comes out of this die, it's a uniform thickness and comes out at the same rate as much as possible across from the left to the right as we're looking at it here. So the first thing we're going to do is we're going to do a flow analysis using the Flow EFD simulation capabilities inside of NX. And as you can see, there's a tag here for Flow EFD called Flow Analysis. And the first step that we'll do is we'll just start the wizard that'll walk us through the process of setting up the analysis. So let me move the part over here. And the first thing it's going to ask us for is a project name. I will call this webinar. And we're going to use the default part. I'll come back and show you a little bit later a modified part that we'll look at a little bit later. When I hit next, it's now going to ask me what units I want to work in. You can see some SI units are available, millimeters, foot-pounds, and so forth. I'm going to pick the USA units, which are feet per second, PSI, pounds, foot, and degrees F. Then it's asking me now what type of analysis we're going to do. Are we going to do an external flow around the part, which is not the case here, internal flow, which is what is selected by default, and that's basically flow inside the part, which is what we want. The flow is inside our die here. So we'll select that, and then we also need to tell the software what other types of things we want to include in the analysis. We are going to toggle on heat conduction in solids, which will, when I do that, you'll notice a couple things. Not only does it give me a check mark there, but it adds an item in my navigator over here, because if we're going to model heat conduction in the solids, we're going to need to find the properties of the solids, the material properties, and so forth that have that conduction occur. Another option here is radiation, time dependency or transient. We won't be using those in this model, but we will turn on gravity. When I do that, it'll show me an arrow indicating the direction currently for gravity, and I can go in and change that. Turns out the negative Z that's shown there is the correct direction for this model, so I'll just leave it as the default. And then there's also rotational capability and a free surface capability that we won't be using in this particular model. The next step is to define the properties for the fluid. You can see we have a number of different types of fluids available in our library listed here. This particular model has a plastic in it. It's a non-Newtonian liquid. So I will open up or expand the non-Newtonian liquid fluids and select this Dow 501 material as my default fluid material. Now for the solids, since we're going to be doing conduction in the solids, again, there's a number of standard materials available to me here, and I could go through different ones there. The one I'm going to pick, though, is under the alloy, and it is a stainless steel material. Initial conditions, or wall conditions, actually is next. Wall conditions are specific conditions that I'd want on walls throughout the model. I can also apply these individually by selecting surfaces within the model if they vary. But I could, for example, define adiabatic walls, heat generation rates, wall temperatures, slip conditions, and roughness, and so forth. So I'm not going to change the default there. The initial conditions is the next item. And you can see there's different thermodynamic parameters I could define, pressure, temperature, and temperature is actually something I want to change. I'm going to start with the melt temperature for the plastic, which happens to be 450 degrees Fahrenheit. And everything else I'll leave as the default. So when I hit finish there, it creates this input data for my Flow EFD CFD analysis. It also shows me on the screen this envelope that represents the computation fluid domain within the model. which is basically a tight envelope around the model. I'm only showing half the model here, so you can see it fits tightly around that. I'll go ahead and turn the display of that off. We don't really need to do anything with it at this point. Now, a couple things that I want to show you as well. Inside of this part, I have created a couple of additional parts. I mentioned that there is an alternate design of the die, which I'll get to in a little bit. But as another couple things that we have here are lids or parts that I've created that close off essentially the inlet and the outlet where the plastic goes in and out of the model. So I don't have to go in and define a separate part for my fluid. I just have to close out where it's open with any type of surface part or solid part that covers that face. You can see they're a little bit bigger than the actual face, which is fine. I will also use those parts as boundary condition selections here in just a second. So let's go ahead and start setting those up. Let's set up a boundary condition, first of all, at the inlet, which is on this blue surface here. And I can go back to my screen and pick that part right off of the navigator if I want. This is going to be an inlet mass flow. I'm going to use a little bit higher flow rate than the default here. I'm going to use 0.75 pounds per second. And if we look at the thermodynamic parameters, it's also picked up that initial temperature value as the inlet temperature value, and I'm not going to change that at 450 degrees F. So when I apply that, you can see the red arrows pointing inwards, indicating that I've got an inlet condition on that surface, making the flow go into the model at that point. We create another boundary condition for the outlet or the opening on the model. And this time I will just select the surface here on that lid that I have created. This is going to be rather than a flow opening, this is going to be a pressure opening. So I'm going to define environmental pressure at that location, and I'm going to take the default values, 450 degrees Fahrenheit and standard pressure, and we'll say okay to that. So that defines the two boundary conditions, just an inlet flow and an opening pressure there. But there are some additional things that we want to define on this model, and those are goals. And the goals are used both to tell it what kind of results we're looking for. So when FlowEFD solves the model, it gives me those results. But it also is used to determine when the solution is complete, when the solution is converged, that it makes sure that these goals that I define are fully converged and give me results that I want. So the first result that I want to see is pressures, and I'm going to select total pressure at the inlet as one of my goals on the model. And then I have another surface goal. I'll put this one on this one's going to be on the outlet. It's going to be velocity. So we're going to get velocity results, and we want the velocities resolved through the model at the outlet. So that gives me 3 goals there. And then the last goal that I'm going to set up is kind of a combination goal. I'm going to, I want to know what the pressure drop is through the die. So I'm going to set up what we call an equation goal. We'll call this pressure drop. And it's going to be a function of the inlet total pressure minus the environmental pressure. Let me double click on that. So we've got, if you look at my equation here, we've got inlet total pressure, and that doesn't look like a minus. So let me repick that. It looks like I picked the wrong thing there. Yeah, it's just the way it looks. I think it is a minus. So inlet total pressure minus the environmental pressure. And I'll go ahead and click on OK for that. So that'll define the pressure drop throughout the model. Lastly, let's take a look at the mesh. By default, it will give me an automatic mesh that gets generated during the solution. And I can edit that. I can take a look, a preview by turning on the showing of the basic mesh. I can increase the level of the initial mesh or decrease it if I want. I think I'll leave it, somewhere here in the middle. The software will automatically go in and refine the mesh to capture fillets and small openings and things like that based on the mesh size I use, as well as I can turn on this minimum gap size, which I'm going to do. And for the minimum gap size, you may want to take a look at a small gap in the model, and whatever I put for that, it will make sure it resolves anything that is larger than that gap size that I specify. It will resolve that. So let me go in and do a measure here, and tells me that's 10 millimeters across that small gap. So I'm going to set, rather than feet, I measured that in millimeters, so I'm going to type in 10 millimeters, and it'll convert that to feet for me, 0.0328 feet. And anything that is that size, it will be resolved with the mesh and included as part of the analysis. So go ahead and hit OK to that, and we can hide the display of the mesh. And that's it. The model's ready to set up and solve. I'll go ahead up here at the top and tell it to run that. This is going to be a new solution. I'm going to solve it on this computer. I could also run it out on a server, and I can tell it how many cores that I want to use. I'm going to use all the cores on my laptop at this point. And I'm not going to wait for it to finish, although it only does take a couple of minutes. But what I will do is show you the monitor that comes up. You can get an idea what it looks like while it's solving. It tells me it's got about 57,500 elements total. About 23,000 of those are fluid and about 34 are thermal. And it goes through, gives you an estimate of how long it's taking and how much longer, a couple more minutes, and it'll be ready. But while that's solving, I went ahead and solved the model ahead of time, and we can start looking at the results on that model. The first thing I'm going to look at is some flow trajectories, and I need to load the results in order to see those. So let me do an animation of the flow trajectories and kind of see, based on the velocity results, how it's tracing those trajectories through the model. Maybe a little easier to see if I turn off the geometry and rotate that. So that's one thing we can look at. Another thing we may want to look at is a cut plot. Let's show that. What that's showing me here is the velocity result. And what we see as we look at, this is on a cut plane showing the arrows as well as colors, indicating the magnitude of the velocity in feet per second. What we see with this, and maybe a little bit concerning with this design, is the fact that the higher velocities are more concentrated in the middle here. We would like to see that spread out a little bit more, and it's not going to, we're probably not going to get that to be perfectly even without a major redesign of this, but we certainly would like to try to spread those higher velocities out a little bit more. And if I add on a surface plot of my pressures on top of that, we'll also notice in this plot, we've got pretty high velocities all throughout that angled area at the inlet. They don't really start reducing until it spreads out here, and they're not real even as well. I'd like to see more of an even line across here on my pressures so that I don't negatively impact the deflection of the die when I look at my structural analysis. Because if it deflects, that's going to, again, give me some irregular or non-even thickness in my plastic as it comes out of the die. So those are a couple of concerns that I have with this model. Let me go ahead and close out. Looks like that thing's solved. We'll go ahead and close that out. But rather than continue with this design, what I'm going to decide to do here is I'm going to modify it. And I showed you, I brought up earlier a brief view of that redesign, potential second design. So let me hide these results. and show you what that second part looks like. So here was my original design. Basically, it comes down at an angle and it comes straight out. My modified design starts in the same location, it comes at an angle, and then it kind of opens up a little bit more before it flattens out. And the idea here is that hopefully with this opening will allow those pressures to dissipate faster and spread out a little bit more, as well as the velocities a little more even across the outside. So whenever you want to redo an analysis with a new part, since it's fully integrated here inside of NX, it's very simple just to switch the part out and apply those boundary conditions and resolve it. And I went ahead and did that ahead of time in the interest of time, and that's what this modified project is. So let me pull up the results of that. And as you can see, I've got some of the same results, the same boundary conditions if we were to look at those. And let's go back. Well, let's just turn off the geometry and look at my cut plot, which was my velocities. And a little hard to tell, but they are a little more spread out. Maybe not quite as much as what I want, but that does look a little better. I look at my pressures. They definitely look a little bit different. We've got the light blue pretty well all the way across here. The red, the pressures are dropping faster in the inlet. And these should be the same colors as what I had on the previous plot. Now, something else I can do here is I can go in and do a compare. See if I have these loaded here. Yeah. So we can compare the one set of results with the other. Let me make this a little bigger so you can see it. There we go. So we can see, I don't think you can see the scale there, but they do look the same. If you zoom in, the maximum is the same. So this is the original on the right. This is the redesign on the left. And you kind of get a better feel for what that fluid shape is, how it opens up a little more and then steps down to the same shape at the outlet as well, just from looking at the fluid by itself. So it does look like, you know, this redesign is going to give us a little bit more even pressure distribution, which should make the deflections look a little bit better. And that's the next thing I want to look at. So let me get out of this compare. I want to do a structural analysis on this part. And the way I'm going to do that is I'm going to export the results from this particular model, the one that I have selected, and I can select the product that I want to export it to. In this case, it's going to be our Nastran structural solver. I can either do an interpolation onto an existing Nastran mesh, which I haven't set up yet. So instead, what I'm going to do is I'm going to export it out on the flow EFD mesh locations, the node locations. I'm going to export the pressures, and the units are going to be meters and pascals. And then what I will do on the structural side is when I read that data in, I'll have it interpolated onto the structural mesh that I'll define here in a little bit. So that file that gets created, I already did this. It's just a format of an XYZ location and a pressure. So these are meters, and this is pressure in pascals. And there is, I think, somewhere in the neighborhood of 13,000 lines of the data from the model that I'll be looking at. So export that out, and now let's look at a structural analysis. So for the analysis, we will go to set up a finite element model for Nastran. The type of analysis will be structural. You can see there's other options available as well. And the bodies I want to use, I need to turn my bodies on if I'm going to use visible bodies. I don't have any on the displayed right now. So let me turn on, I'll turn on the modified model. And you can see that this is the one that has the step in it. You rotate it the way I've been viewing it, which is this view here. Let me get back into my creating my FEM. We're going to only use the visible bodies. There's 3 other bodies that are there available, but we're only analyzing this particular one. I don't need my lids because those were really just used to enclose the CFD volume. And for the solution name, we'll call this webinar. And I think that's the only change I need to make on my solution. Okay, so the first thing I want to do is define the structural mesh. As you can see, there's a number of options, types of meshes you can create in SimCenter. I'll be using a 3D tetrahedral mesh, makes the most sense for this type of geometry. You can also create 2D meshes. You can create a swept mesh we'll give you hexahedral or brick elements, beam elements, and there's other options as well. And you can even manually go in and create nodes and elements or manually extrude and revolve elements as well. So a lot of meshing capability there that I'm not going to get into today. The other thing that happens too, let me just pull up the 2D mesh form, is depending on the solver that you select, we have the language built in for that solver. So this is showing me only elements that are available for Nastran. Had I selected another solver, it would show me elements specific to that solver. So it always, not only the elements, but the boundary conditions as well will show up in terms of what will get created for that particular solver. So let's go ahead and create the 3D mesh. And I'm going to use the TET10 element, the parabolic tetrahedron. I'll use a mesh size of 15 millimeters. And then I'll leave the quality check, the curvature variations, and some of the other things at their defaults. One thing I do need to change is the collector, which tells the software what material to use. So I'll set up a new physical property table, and I'll pick a stainless steel material out of our library here. So in the Nastran library, there is a stainless steel right there. We'll use that. And we can call it steel. And we'll go ahead and generate the mesh. So for Nastran, you generate the mesh before the solution on the part. So that we'll actually get to see this mesh. And it looks pretty good. It automatically refines the mesh around curvature. You can see a little finer mesh around these holes here. But in general, the only thing that I defined was that I'm going to try to create elements that on edge measure 15 millimeters. If I wanted more control, there's a number of mesh controls that I can put in here. I can specify a specific side on an edge. We can do biasing. We can specify size on a face. We can even set up boundary layers, so layers of elements next to a wall. And we can also even define a bounding volume where you pick a volume inside the part and refine the mesh or coarsen the mesh in that area as well. So just for this model, I just used the global size of 15, and that's all I define. And then I've got 2 boundary conditions to set up. The one we've been talking about, which is going to be the pressure load that came from the flow EFD model. So let's go ahead and do that one first. It's going to be applied on element faces that are inside where the plastic is pushing, inside this die. And the easy way to go and pick those element faces is setting my selection tool here to feature angle elements. And what that's going to do is if I pick an element face, it's going to grab any other elements that are within a 30-degree tolerance of being tangent to that face. And so if I go in and pick one of these, it essentially gets that entire surface there. And go ahead and select some more of these to get the rest of it. You can apply boundary conditions to geometry, which you'll see me do in a minute when I apply the constraint. The reason I'm not doing it in this case is I need these node and element locations to map those values from the flow EFD model onto this model. So we can get the rest of these faces. There's one there for that lip and that one, and that should have all of them covered. Now for the pressure value, I'm not going to put a constant pressure in. We want the pressure to come from that result file from FlowEFD. So I'm going to set up a table field, and it's going to be a function of the Cartesian coordinate X, Y, and Z and pressure, except that if you remember when I was setting that up, the units were meters for the X, Y, and Z coordinate, and the pressure was in pascals. So let me set those units up, and then I'm going to go and pick that, result file that I exported, is right there, and it'll bring that in. And as I mentioned before, I think there's like 13,000 lines in this. So it's brought in all those values. And when I hit OK, here it'll map those onto the node and element locations of my structural mesh. And if I want to kind of verify those, I can do a contour plot of that boundary condition just to view and see that, yeah, this does look like what I had here on my FlowEFD results. The other boundary condition that I want is the constraint. I'll turn off the elements for that and set up a fixed constraint, and it's going to be on the holes on the top and bottom here. And I should be able to just do a window around those holes to select them. Total of 64 faces. There's 16 holes on the top and the bottom, and I think there's, so that's 32 plus the bottom face is 64, and that looks good. So that's the fixed constraint. There it is. And the model should be ready to solve. Let's go ahead and solve this one. It takes less than a minute, so I'll go ahead and let it run while we wait here and show you what happens during the structural analysis solution as well. So first it goes through and writes the model out. And let me move this solution monitor over. Looks like it created about 250,000 tetrahedron elements, 261,000. And the nodes created were about 388,000 nodes there. And we've got the pressure load on 66,000 faces. We've got 23,000, I believe that's the nodes being fixed there. So as it's solving, we can look at a graph of the convergence. And you can see it's converging pretty quickly here. And within just about 30 or 40 seconds, it's converged, and we have our structural results. So let's close these windows out. And normally with the structural analysis, we might be more interested in stresses, but on this particular model, I know that I'm not going to be anywhere close to yield stress on this material. So I'm more interested in looking at displacements. So let's take a look at those. So let me turn off the exaggeration that comes on by default and the element display. And these are the displacements. And they kind of match the pressures. And if you think about it, it does make sense that you have a little bit more displacement on the bottom than the top because there is less material on the bottom stiffening it. There's a little more material here as we look at it on the top, so that's why it's slightly less. But overall, my goal was to keep this under 0.1 millimeter deflection, and we've done that. So it looks like this new redesign is going to work for this design. We can also look at cutting planes through this model, although they're fairly constant. But as you move this plane around, you can dynamically have it update as you slice through and just verify the different areas of what the displacements may be. If you want to, something else you probably would want to do with this model is find out what all the displacements maybe are on this face. So to do that, we can go in and set my picker to be a face, pick a face, and it will list all the different values, and there's a lot of them there with the mesh size I have that's listed, but the good thing here is it tells me the min, the max, which we knew was 0.0659. The average is 0.031. We can also export this out into Excel if I wanted to use this or see this in Excel for whatever reason. I can export it to a text file. I can save that selection as a group as well, or create a field from that to use it in some other area in analysis. So, and I think that's pretty much it. I think I'll turn it back over to Pat at this point to summarize what we've talked about today. Pat?
Yeah, thanks, Tim. Good job. Let me get my screen back here. All right, so yeah, thanks again, Tim, for that. That was a really great demonstration there. And as you just saw in Tim's demo, both the flow and structural simulations were embedded within the CAD environment. So that makes it easier for a design engineer to learn and navigate the workflow. This also allows for the flow and structural models to be associated to the base NX CAD model. So as you mentioned, any design changes that you do can rapidly be reevaluated with minimal rework. Finally, you can easily chain analyses together so that results from one analysis can be applied as input to another type of analysis, such as we saw with the pressures from the CFD result being applied to the structural model of the die to check the deformations of the exit opening. Just to go over a couple of customer examples here, let me get my slide change, there it goes. Guangxi Yuchai Machinery, the largest producer of internal combustion engines in China, uses simulation-driven design to help them meet market demands for more personalized products. Greater personalization means more product categories, but with limited dedicated CAE resources, it became impossible to promptly feed CAE analysis results back to design engineers. But by implementing simulation-driven design methods within the designer's NX CAD environments, Guangxi Yuchai Machinery's designers could begin using simulation to get immediate feedback on how their designs will perform. And Mitsubishi Materials Corporation used simulation-driven design to study various design variants to optimize the liquid cooling channel opening to improve cooling performance for advanced cutting tools. Even though Mitsubishi Materials doesn't have specialist CFD analysts, their designers were able to perform the basic CFD analysis within their CAD environment and ultimately achieve an 11% increase in flow rate through their cooling system. So in summary, out-of-the-box NX CAD embedded simulation helps you quickly assess the performance of your design for structural integrity, kinematic and dynamic motion, and fluid dynamics and heat transfer. The simulation all takes place in the same NX CAD environment, so you don't need to learn a completely new user interface or deal with messy data transfers. And finally, the simulation is based on trusted SimCenter technology, so your analyses can scale to high-end simulation experts for further analyses. And before I finally conclude this presentation, I just want to again remind you that the previous webinars on simulation-driven design are available on demand from the Siemens PLM website, and today's webinar will also become available shortly, probably in the next few days here. So with that, again, thanks everybody for taking the time to join the webinar today. Let me open it up to Sarah. We'll